Hey guys, I hope you guys are all doing well. Today, we're going to be talking about a couple of tests to determine whether or not a series converges or diverges. There are a couple that you guys need to know. We're going to cover quite a few, and we're on our second and third test. We just went over geometric series tests. Now we're going to talk about the integral test and the p-series test. Without any further ado, the integral test, this is it as follows. If f is positive, continuous, and decreasing for every x that's greater than 1, and a sub n is equivalent to f of n, then we know that this series and this integral will also converge or diverge. If this converges, this also converges. If this diverges, then this diverges. And so we have to check a few things off our list when we're running this test. It has to be positive, continuous, and decreasing. Okay? So let's take a look at this one right here. We're going to write out a few terms just to make sure we know what's going on. We're going to plug in 1, 2, 3, 4 as we go. And so as we go to write out this sum, we plug in 1. We're going to get 1 over 2. Plus the next one, when we plug in 2, we're going to get 2 over 5. Okay? If we plug in 3, we're going to get 3 over 10. So if we look at this, we're going from a half to a little less than a half, to a little less than that as well. It keeps decreasing. So first off, all of our numbers are in fact positive. Okay, decreasing. And continuous. On the interval. Why is it continuous on the interval? Well, if we go over here and we take a look at this interval, we're going from 1 to infinity. If we look at the denominator, n squared plus 1 always works for real numbers. So there's nothing that's going to make this not continuous. So because of this, we know, sorry, my dogs are barking a little bit. What's going to end up happening is we're able to take the improper integral from 1 to infinity of n over n squared plus 1. Okay? dn. When we take an improper integral, we must rewrite it as the limit as b approaches infinity of the integral from 1 to b of n over n squared plus 1, dn. The one issue that we're going to run into this is, if you're looking at it, first thing we look at, we have n squared in the denominator. We have n in the numerator. So if we take the derivative of n squared, we should be getting 2n. But if you look up here, we're missing a 2. So we have to put in a 2. And then we have to multiply the outside by 1/2. And then this reaches the point where we have u prime over u. So this is just going to be an ln problem where we have the limit as b approaches infinity of 1/2 ln of n squared plus 1. We don't have to put absolute value around it because n squared is always going to be positive, so we don't have to worry about it being negative. And then we're going to evaluate this from 1 to b. If we do this, what's going to end up happening is we're going to get the limit as b approaches infinity of 1/2 ln of b squared plus 1 minus 1/2 ln of 2. And the thing about this is, as b approaches infinity, this entire thing is going to also approach infinity because ln of x, it works like this. It's going to be increasing over time slowly. And so what's going to end up happening is this approaches infinity, and this is still going to be 1/2 ln of 2, which means that the function, the integral, diverges. Okay? And then what we have to do is go out and write y. So since the sum is positive, decreasing, and continuous, on the interval then either both the series from n equals 1 to infinity and the improper integral from 1 to infinity converge or diverge. Okay, I'm just explaining kind of what we need to know from the prior section. I'm going to add a little page here. And then what you guys really just have to write is, since this all occurs, since the integral from 1 to infinity of n over n squared plus 1 diverges, then the sum from n equals 1 to infinity of n over n squared plus 1 must also diverge by the integral test. Okay. The blue part is the part that's important. If it's able to apply because it's positive, decreasing, continuous, then we're able to apply the integral test. We applied the integral test. We found that the improper integral diverges, which means that the series also diverges. Okay, and that's the basic concept. What we're going to do is go down to the next one. Let's see what happens. Okay, use the integral test to determine convergence or divergence. Okay, so first off, let's go ahead and write a few out. We have to ensure that they're always going to be positive. It's always going to be decreasing, and it's going to be continuous on the interval from 1 to infinity. Okay, with this, we're going to get 1 over, if we plug in 1, we're going to get 1 over 2 plus 1 over 2 squared plus 1 is 5 plus 1 over 10. So it's looking very similar to the prior one. Okay, so first off, we know that it's going to be positive. Okay, decreasing. And then we have to show that it's continuous. Well, if you look at the interval from 1 to infinity, in the denominator here, we always have the function value squared, n squared, the function value n squared. It's always going to be positive. So there's no issues with having a positive number cancel out positive 1. It'll always be continuous on the interval from 1 to infinity. And so from that, what we're able to do is this means we're able to apply. We can apply the integral test, which states that if we take the improper integral from 1 to infinity of 1 over n squared plus 1 dn, then either both these converge or both diverge. Okay, what's interesting about this one is we don't have an ln like the last time. There's no n in the numerator, so we're not going to have u prime over u. This is actually going to be an arctan, so we have to rewrite it first. The limit as b approaches infinity of the integral from 1 to b of 1 over n squared plus 1 dn. And we're going to go through and we're going to evaluate this. And we're going to get arctan of u over a, which is going to be n over 1. Arctan of n, evaluated from 1 to b. Okay. So here's the thing. Arctan, we need to know what it kind of looks like. So we're going to have arctan of b minus arctan of 1. Arctan is asking when is the function, or when is tangent going to be equal to that? Well, tangent's equal to positive 1. If you guys recall, arctangent only works in the first and second quadrant. We know that's going to happen up here at pi over 4. This is going to be root 2 over 2, root 2 over 2. It only works in the first and fourth quadrant. So pi over 4 is going to be what this section is. To do the left-hand side, we have to kind of know what arctan looks like. Well, arctan is bounded between negative pi over 2 and pi over 2. And it looks something like this. So as we approach infinity, our y value actually approaches a number. It approaches pi over 2. So we're going to end up getting pi over 2 minus pi over 4, which is going to give us pi over 4. Let me go ahead and add another page to this just so I don't keep running over stuff. And so we're going to end up with pi over 4. Okay, so what this means is this converges. Okay, so we have to go through the same sort of thing where we go and explain that since one converges, then the other must also converge. So since the integral from 1 to infinity of 1 over n squared plus 1 dn converges, then the sum from n equals 1 to infinity of 1 over n squared plus 1 must also converge by the integral test. And that's it. All right, on to the next part. This is called the p-series. P-series, it's not the PewDiePie meme, guys. It's not that. It's not T-series, it's P-series, okay? Whatever happens with this, you get this function. It's 1 over n to the power of p. This is going to be called a p-series, okay? P-series, they look like this. You can have 1 over n. N can be any number, right? It goes from 1 all the way out towards infinity. Okay, and then as for the next part, if you have 1 over n, this is called the harmonic series. This is going to be an important series, and we're going to show why in just a moment. So let's go ahead and scroll down. So here's the convergence of a p-series. It converges if p is greater than 1. It diverges if p is between 0 or is equal to 1. So if we're looking in each of these, we're able to go through, and we're able to actually go through and put this all the way to the power of 1. This entire thing's to the power of 1. You can even treat it as just n to the power of 1 in the denominator. Whenever we have something like this, this is going to diverge. Why is it going to diverge? Okay, let's go through and apply the integral test to it. What we know with this is that if we plug in 1, we're going to get 1. If we plug in 2, we get 1/2. If we plug in 3, we get 1/3. So we know it's positive, decreasing, and continuous from 1 to infinity. So let's go ahead and take the integral. The integral from 1 to infinity of 1 over n dn, this is the harmonic case. This is going to be a great tool for us to use when we get to comparison tests. When you take this integral, we're once again have to rewrite it beforehand. We write it as the limit as b approaches infinity of the integral from 1 to b of 1 over n dn. When we do this, we get the limit as b approaches infinity of ln of absolute value of n evaluated from 1 to b. When we do this, we're going to plug in b. And you guys are going to see really quickly, if we plug in b here and take the limit, we're going to get ln of infinity, which diverges. We're going to get infinity minus 0. So it's going to diverge. Okay? And because of this, since this diverges, then the harmonic also diverges. And we're learning that in all these cases, this is going to be a p-series case. If we just look at it and see that this exponent right here is 1, that we can just write that this is a p-series where p is less than or equal to 1, so it diverges. We can simply go and write that when we see that it's a p-series. Okay. let's go ahead and take the case where it's 1 over. Let's go see what happens. Let's apply the integral test to it just to see what happens. Once again, we're going to get 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. So you can see that it's decreasing. It's continuous on the interval from 1 to infinity. 0 is not included on that interval. And then we also know that it's positive. Positive, decreasing, and continuous. So we can apply the integral test. So we're going to take the limit as b approaches infinity of the integral from 1 to b of 1 over n squared dn. Let's go ahead and rewrite this. To take this integral and rewrite this as n to the negative 2 power dn. Okay, so when we integrate, we follow just the basic power rule, and we're going to get limit as b approaches infinity of n to the power of negative 1 over negative 1 evaluated from 1 to b. If we go through and rewrite this, what's going to end up happening is we're going to get the following. The limit as b approaches infinity of negative 1 over n evaluated from 1 to b. Let's go ahead and substitute, and we're going to get 1 over b minus negative 1 over 1. And we have to take the limit as b approaches infinity of this entire thing. If we do that, what's going to end up happening is we're going to get this part here approaches 0 because the number over infinity is 0. And this is just going to leave us with 1. So we're going to have 0 plus 1 or 1. So this means that it converges. And if the improper integral converges, that means the series also converges. Just like in the last case, when you notice that this exponent here is bigger than 1, you can say that it's a p-series, where p is greater than 1, so it converges. And that's it. We don't have to say anything more. And why is that? Because we've applied the integral test in both these cases. We see that when n is less than 1 or equal to 0, somewhere in between less is greater than 0 and less than or equal to 1, then it diverges. Okay? And that's how we do that. Okay? And then we have one last one right here. This one's a little funky. You've seen this before. If you look at it, we have to plug in a few numbers, see what's going on. Right now we have the integral test, and this is not a p-series. So we're going to go through, and we're going to plug in some numbers, see if it's positive, decreasing, and continuous. Well, ln is discontinuous at 0, right? Because the ln function, it looks like this. At 0, it's going to approach negative infinity, so that doesn't work. But we're going from 2. So we're going to be out here. We're going from 2, and we're going on. Okay? When we plug in numbers to this, we get 1 over 2 ln of 2 plus 1 over 3 ln of 3, which is smaller because we're dividing by something larger, 1 over 4 ln of 4. So far what we know is it's positive, continuous on the interval from 2 to infinity, and we know it's decreasing because the numbers in the denominator are getting larger. So what we're able to do is take the improper integral from 1 to infinity of 1 over n ln of n. And I'd like to rewrite this just a little bit. We're going to go through, fix the improper integral, limit as b approaches infinity of the integral from 1 to b. We're going to rewrite this as 1 over n ln of n in the denominator. And you guys are going to find that if we take the derivative of the denominator, we're going to get 1 over n. We're going to get u prime over u. So we integrate this. This is that problem that we've gotten before where you have ln of n evaluated from 1 to b. Okay? Now, I'm just going to tell you guys this. When you take the limit as this approaches infinity, you get ln of infinity. So it approaches infinity. And ln of infinity approaches infinity because the function, once again, looks like that. And so we end up getting that this diverges. And thus, hey guys, thus by the integral test, both of these must diverge. Okay? So since the integral from 1 to infinity of 1 over n ln of n diverges. Then the sum, Opal, stop it. I'm almost done. 1 over n ln of n must also diverge by the integral test. So a powerful test to fall back on, guys. And I hope that this went well, guys. After this, please work on your practice problems that I have listed for you guys in Google Classroom. Hope you guys have a beautiful day. Bye.